Hi guys, today we're going to learn more about power series. Why do we care about finding a Taylor series for a particular function? Such as the problems that we did yesterday and in previous lessons and the problems that you maybe did for homework. For instance, why is so important to know that we can write sine of x as x minus x power 3 divided by 3 factorial plus x power 5 divided by 5 factorial minus x power 7 divided by 7 factorial plus ... As you know, trigonometric functions lack finite algebraic formulas, so power series are the next best thing. So using power series allows you to find an approximation. It's very accurate, okay? The values of trigonometric functions as well as other transcendental functions. Okay, so in this example, what they want you to do is use a Maclaurin series for sine of x to approximate sine of 1 so that the error on your approximation is less than 1 over 1000 without using your calculator. So they want you to justify that your error is less than 1 over 1000. So this is looking like the alternating series test, and especially the error bound. Okay, so what we have here is you are obviously going to use the sine of x that it's given to you here, and what they want you to do here is compute sine of 1 like an approximation. So what you know is that sine of 1 is going to be approximately what you plug the 1 in instead of the x's. So what you have here is going to be 1 minus 1 to the power of 3 divided by 3 factorial plus 1 to the power of 5 divided by 5 factorial, and then you have minus 1 to the power of 7 divided by 7 factorial plus ... Okay, so what you want here is to have a really good approximation, or at least an approximation where the error is less than 1 over 1000. Okay, so you're going to ask yourself, so we have this. Which one is the truncated term? Remember that back in the day we had the truncated term, so we need to find the truncated term. So you do know that 3 factorial, so this is because we know that 3 factorial, the ones are just ones, right? So you know that 3 factorial is 6. We do know that 5 factorial is 120, but you might know that 7 factorial, that's huge, it's 5040, okay? So plus ... So what you recognize here is that you do have the truncated term. This guy that you have here is your truncated term, so you can do the little line here, okay? Because this one is going to be your truncated term, okay? So that's what we have. So the approximation that we want, that it's less than that, okay, is going to be sine of 1 is going to be approximately 1 minus 1 over 6 plus 1 over 100, and that's going to be the approximation with an error less than this, because what you know is that what did you learn before? You learned that the error, okay, is less or equal than the truncated term. Here the truncated term is going to be negative 1 over this, which you do know that it's less than 1 over 1000. So we have this equation. To prove this, what you have, and by the way, this approximation that we have here is going to be 101 divided by 120. Okay, if you want to, you can leave it like this, but in case that, this is my approximation. Okay, but we need to justify this. To justify that we can use the truncated term, what do you need? You need to make sure that the series that we have is basically converges via the alternating series test. Okay, so what you know, and we can pretty much write this as follows. You know that this is going to be equal to the summation from n equals 0 to infinity of what? You have that it's going to be negative 1 to the power of n x to the power of 2n plus 1 divided by 2n plus 1 factorial. Are we okay with that? So that one we're going to apply the alternating series test. So you do know that that series that we have over there, first thing, terms, okay, alternate in sign, Okay, check. Second condition, you do know that the terms what? Decrease in magnitude, which is true. Check. Okay, and the third condition, you do know that the limit when n approaches to infinity of, in this situation, is going to be a sub n is going to be equal to 0, which is a check. Okay, so therefore, okay, this is true. Okay, thus by the alternating, this is true by the alternating series remainder theorem. Okay, so we have that. Okay, so because this is the truncated term. Okay, so now they want you to use your calculator to find the actual error in my approximation. So the actual value, okay, actual value is going to be sine of 1, right? So for that one, let me get my calculator. And where's my calculator? It's here. Okay, so what I'm going to do here is I just do the sine of 1, right? Okay, so if it gives you sine of 1, remember you can always put the dot. So you have here the approximation. Okay, so not the approximation, the actual value. Okay, so I just copy this with all the dots. Yes, so you know that that's the actual value. You know that the error is going to be what? Actual, okay, minus approximation. Okay, you are going to tell me, hey, where's my approximation? Well, here's your approximation. This is approximation, the one that we have here. So what am I going to do here? Complicated situation? No, you copy that. So minus, and what was my approximation? We say that it was 101 divided by 120, right? So you have that. Here, as you can see, it's complaining because it's rounding somehow. But you just need, as you can see, it's rounding horribly here. So I really don't like this notation. It's absolutely horrible. So I would just write it as negative 0.00. How many zeros we have? 1, 2, 3. Okay, 0. And then you have 195, and that would be more than enough to see that the error is quite small. Okay, so that's what you have for the actual value. Okay, so let's move on to the next question here. Find in series form an antiderivative for sine of x power 2, and then use it to approximate this so that the error in your approximation is less than 1 over 1000 without using your calculator. Okay, so we know from yesterday's lesson that sine of x squared, it was equal, you just plug, instead of the sine of x, you plug the x squared, you substitute that, so you have x squared minus, and it was going to be x squared to the power of 3, which is 6 divided by 3 factorial, plus x power 10 divided by 5 factorial, minus x power 14 divided by 7 factorial. Why I'm doing this? Remember that yesterday for this problem, what we were doing, we were just plugging the x squared instead of this one, this one, this one, and this one. That's why I have 2 times 3 is 6, 2 times 5 is 10, and 2 times 7 is 14 that you see here. Okay, if you are wondering what in the world she's doing. Okay, now we have this. Now they are asking you to, okay, from this one, okay, from an antiderivative, okay, then use it to approximate this. Okay, so what do you want to find? You want to find the integral from 0 to 1 of sine of x squared, okay, dx. Okay, so that's what we want to find. So what are you going to do here? Well, you can easily substitute, okay, the sine of x squared for this situation that we have over here. So you have from 0 to 1, and then use a big bracket here so you can be more free with the space. Okay, so you just replace the sine of x squared for the polynomial that you have. That's the idea. Okay, so that's why we want the beautiful Taylor polynomials here. Okay, and the x. Okay, now ask yourself, okay, this looks like a lot, I know. Can you integrate each one of these terms individually? I think so. Oh, we have the factorials. Leave it like that. Okay, so take it simple. Okay, step by step. Okay, so what do you have that it's going to be the integral of x squared? you know that it's x to the power of 3 divided by 3 times nothing, okay? So this one is times 1. Minus, and then you have x power, what's that? 7 divided by 7 times 3 factorial, okay? Then you have plus x power 11 divided by 11 times 5 factorial, okay? Then what do you have here? You have negative, okay, x power 15 divided by, what's that, 15 times 7 factorial, which you know that this one is humongous, okay, plus dot, 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 okay. So you have here, let's say that you don't realize, okay, 0, 1, okay, and you keep putting stuff, okay. So here, what are you going to do? As we were doing with the first fundamental theorem of calculus, you're going to, you know, replace the x's for first the 1 and then with the zeros. The beautiful part is when you replace the zeros, everything goes kaput, okay? So what do you have here? So what you have here is pretty simple. You have a 1 over 3 minus, and then you have a 1 over 7 times 3 factorial, which is 7 times 6. Then you have that this one is going to be plus 1 divided by 11 times 5 factorial, which you know that this one is going to be the truncated term. Why it's truncated term? Think about something. This is my brain thinking, right? You know that 11 is quite big, and then you have 11 times 120. What's that? That is greater than 1000. Do you agree with that? So this is your truncated term. So let's do the lines here so you do know that that's your truncated term. Plus dot, 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 right? Okay, so that one, huge, okay? I don't even pay attention to this one because this one is ridiculously big. If 7 factorial was what? 5040, imagine times a 15, that's huge, okay? So the error will be super small, okay? As you can see, because the denominator will become big, okay? So this is going to be your truncated term. Do you agree with that? So what you know is that you want how many terms in this equation? Only 2. Great. Okay, so you have that it's going to be your super approximation here that they are talking about is going to be, this is the approximation, that's why I put the squigglies. Okay, it's going to be only 1/3 minus, and you have that it's 1 over 7 times 3 factorial. Do you agree with that? So this one you can easily have 1/3 minus 1 over 42, which we can easily compute that it's 13 over 42. Do you agree with that? So this is your approximation. Remember, this is an approximation that you have. Okay. While we can apply the alternating series remainder theorem because it says justify your answer, right? So you can justify this because you have first condition terms. What's the business here? Alternate in sign. Okay. Second condition that you have in from that series. Well, I'm here writing the third one. But no, let's do it in order so you can remember them. I mean, you can do it out of order, but I want you to remember these terms. Decrease in magnitude. And what's your third condition? Your third condition is that the limit when n approaches to infinity of the nth term is going to be equal to 0. So check, check, check. So what you have is that the error, okay, is going to be less than the truncated term. What was the truncated term? It was 1 over 11 times 5 factorial. Yes, absolute value, and this is less than 1 over 1000. Yes or no? So you have this by the alternating series remainder theorem. Okay, so that's what you have for this problem. Okay, so yeah, let's move on to the next part. So for this part of the problem, they want you to use a calculator to find the actual error in your approximation. So what are you going to do? Well, the first thing that you're going to do is find the actual value. The actual value, you are going to find it in your calculator. Okay, so let me clear my calculator so we have a clear start here. Okay, so you go to calculate. Okay, so what are you going to do that it's the actual? Well, let me put what's the actual. The actual value is the integral from 0 to 1 of sine of x power 2 dx. Okay, So as you can see, we cannot do it by hand because the use of it would be disgusting. There's no use of. Okay, so you go to calculus, then integral, then you have from 0 to 1. Okay, then you type your beautiful sine function there, x power 2. Okay, and then your dx here. Do you see it? Okay, so you have that it's going to be copy that value. That's the actual value is 0.31026.8 and dot 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 dot. Okay. So please remember, in case that you forgot, let me put the approximation. It was 13/42. Okay, so that's a very nice number. Okay, so we can do this value. Okay, minus and use parentheses. Well, I don't know why that's using the other one. 13 over what was it? 42, right? So you have that. Okay, so I would copy that my error. Okay, that you know that the error is actual minus approximation. Okay, is going to be equal to that value that my calculator gave me. Okay, it's 0.000744. Okay, so that's going to be my actual error. Okay, you can see that the error is quite small again. Okay, and this is all because of the beautiful alternating series remainder theorem. Okay, so the last example that we have for today is you need to write a Maclaurin series for the function e to the x, and they want you to give the first 4 non-zero terms and the general term. So as you know, we can do it by hand. So in case that you forgot how to do it, you should have memorized it, but if you did not, I'm going to show you again how to get it by hand. What's the derivative of this one? E to the x. What's the derivative of that one? E to the x, right? So you can see dot 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 dot, you are always going to have e to the x. Since it's Maclaurin, you know that it's centered at 0, so you have that it's f of 0 is going to be what? 1. F prime of 0 is going to be what? 1. F double prime of 0 is going to be also 1. So dot 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 dot, you can see that, okay? So you know that e to the x is going to be the Taylor polynomial, okay? Centered at 0 is going to be what? 1 plus x divided by nothing plus x squared divided by 2 factorial plus x power 3 divided by 3 factorial. How many terms? 4. 1, 2, 3, 4 plus dot 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 dot. Okay, you have that it's going to be x power n divided by n factorial, and I don't know why I didn't put the factorial there, but make sure that you double check, okay, in case that you are like your teacher that forgets the factorial just because. Okay, so you have this, and you know that it's for all x's. Okay, so you have this. Now they ask you this one that it's very interesting. Use your answer to A to find the limit when x approaches to 0 of f of x minus 1 divided by 2x. You are like, okay, so this, what we have here is let me erase this for the sake of the space. Okay, so you do have that all of this is f of x. Okay, whether it likes nice or not. Okay, so you have two ways of doing it, and I'll do both ways. If you want, you can replace, technically speaking, all f of x as the polynomial or as e. So we have two choices. Okay, so choice number one, without without replacing the e to the x, you would have that technically speaking this is the limit when x approaches to 0, and then you would have here 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus dot 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 plus x to the power of n divided by n factorial plus dot 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 dot, close it. Then you will have a minus 1, and all of this you would have it divided by 2x. Do you agree with that? So you can see that this one and this one, they go away. So what do you have here left? You have the limit when x approaches to 0 of what do you have here? You would have x plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus dot 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 x power n divided by n factorial plus dot 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 dot. All of this divided by what? 2x. Okay, so what you can recognize is that we can cancel the x. Okay, so here I'm doing step by step so you can see every single step. So what happens? In this term you have that this would be a 1/2. Do you agree with that? this term that you have here, it would be a plus x divided by, what would be this? 2 times 2 factorial. Then the following one, what would be the situation here? It would be plus x power 2 divided by 2 times 3 factorial plus dot 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 dot. Okay, then what would you have here? You would have x to the power of n minus 1 divided by 2 times n factorial plus dot 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 dot. Okay, so this is what you have. Cool. Now, if x is approaching to 0, what happens to this guy? That's 0. What happens to this guy? That's a 0. The dot 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 dot, zeros. How about this one? Zeros. For the rest of the time, zeros. So what do you have that it's this? This is a 1/2. Are we okay with that? So yay, we are done via the Taylor polynomial. Now, let's say that you did not want to use the Taylor polynomial. So the second way to do this is the following. You have the limit when x approaches to 0, and then instead of f of x being the polynomial, you would put the f of x being e to the x. So you would have e to the x minus 1 divided by 2x, right? So if you plug the 0, what happens? You have what? 0 over 0, right? Do you agree with that? So with L'Hopital, you would have that limit, okay, of x approaching to 0 of e to the x minus 1, that's going to be equal to 0, and the limit when x approaches to 0 of 2x is going to be equal to 0. Okay, so this, okay, produces what produces an indeterminate form in the form 0 over 0. So okay, we can use L'Hopital. Okay, we can use L'Hopital. Okay, so what happens here? You apply your L'Hopital's rule. Okay, why? Because we were having an indetermination in the form 0 over 0. Okay, so the derivative of e to the x minus 1 is just e to the x, and the derivative of 2x is going to be just 2. Are we okay with that? So now you replace the x for the 0, and what do you have? What a surprise, we have exactly the same result. Isn't that super beautiful? So I hope that you find this video helpful. Bye!